We have so far been discussing separable equations, but now we are going to see a class of equations which are not themselves separable, but they can be turned into separable equations if we apply a particular transformation. And this is the class of homogeneous equations. And this is the definition of homogeneous equations. Look at this first order differential equation. This is what we have been considering so far in the differential form. M dx plus n dy equal to 0, where m and n are both functions of x and y. So when you express this equation in the derivative form, it of course looks like this: dy dx equals some function f of x comma y. Now we are going to call this differential equation homogeneous if, when we express it in the derivative form, there exists a function g such that this right hand side can be expressed in terms of g like this: g of y divided by x. If this happens, then we call this equation a homogeneous equation. Consider this example 210 and look at this differential equation here: x square minus 3y square dx plus 2xy dy equal to 0. And this is a homogeneous equation. When you express this equation, which is in differential form, in derivative form, it is this: dy dx equals 3y square minus x square divided by 2xy. Why is it homogeneous? Because this right hand side is a function of y divided by x. Because we can express the right hand side like this. You can see for yourself, if you do the division, it is 3y square divided by 2xy, or 3y divided by 2x minus, after cancelling this 1x from the numerator and denominator, the second term is this minus x divided by 2y. Now you can write the first term like this: taking y divided by x apart, 3 divided by 2 times y over x, and in the second term you write minus 1 divided by 2 separately, and in place of x divided by y you write the reciprocal of y divided by x, because that's what it is. So ultimately this entire expression becomes a function of y divided by x. So that function is that g there. So because we can express this right hand side as the function of y divided by x only, that is why by definition the original differential equation is homogeneous, or this is homogeneous because they are essentially equivalent. Let's consider another example 211, and here the differential equation is this: y plus square root of x square plus y square dx minus x dy equal to 0. This is also homogeneous. When you express it in the derivative form, it is this: dy dx equals y plus square root of x square plus y square divided by x. But how is it homogeneous? Now we have to express this right hand side as a function of y divided by x. So we start expressing this right hand side as a function of y divided by x. The first step is obvious: you divide each term by x. So automatically here you are getting y divided by x. This, however, causes a little problem. You see, because x is appearing in the denominator, x is not 0, but x can be negative also. So in place of x, if you write the absolute value of x, then you are writing a positive quantity. If x is originally positive, this is equal to this. So then you can write plus here. But if x is originally negative, say minus 2 for example, but you are writing 2 here, then where will that minus sign go? So for that you have also kept here the possibility of having minus. So this plus or minus has to be interpreted like this, depending on the sign of x. That is, you would consider plus here if x is positive, but you would consider minus here if x is negative. From another point of view, this is how also you can think of this situation. You do not think, you do not start here and reach this. It's a little confusing that way. Instead, you look at this and try to see if you get this back. If x is positive, by definition mod x is x. So then you are considering plus and you are having this. But if x is negative, then mod x by definition is minus x. In that case, here you are considering minus. Minus and minus give you plus back. So that's how you have this thing. But why did we introduce this mod x here? That is because we want to take the x inside the radical. And if you remember, mod x is actually equal to the non-negative square root of x square. I am not going to deep into, it's not really anything deep, but I am not going into why this is equal to this. This you should know. So now you can take x square inside, and when you do the division, x square divided by x square gives you 1. And in place of y square divided by x square, you can write the square of y divided by x. So that's how you have been able to express this right hand side as a function of y divided by x only, and that is why that equation is also homogeneous. With these two examples, it becomes clear that in order to show that a differential equation is homogeneous, it's a little cumbersome to every time go through this process of first of all turning the differential equation into the derivative form if it is not originally in that form, and then you express the right hand side as a function of y over x only. It takes some time to do all these things. Is there a better way of deciding if a given differential equation is homogeneous? Yes. For that, let us first of all define a homogeneous function itself. Say you have a function f of two variables x and y. It is said to be homogeneous of degree n if when you replace x with tx, t is some other variable, some parameter, something, and you replace y by ty, then you can take t to the power n outside, and whatever you will be left with will be your original function expression f of x comma y. If this happens, then we call this f homogeneous of degree n. What does this have to do with those equations and their homogeneity? Let's see. Suppose that two functions m and n in this differential equation m dx plus n dy equal to 0 are both homogeneous and of the same degree n. Alright. Now let us see what we get from the homogeneity of m and being homogeneous of degree n. So m being homogeneous means what by this definition? That if you replace x with tx and y with ty, you will get this t to the power n times m of x comma y. In particular, if in place of t you take 1 divided by x, what will happen here? You will get 1 because this is tx and t is 1 divided by x. Here you will get y divided by x. Here you will get the nth power of 1 divided by x, and this of course is just m of x comma y, or if you multiply both sides by x to the power n, this is what you get. M of x comma y equals x to the power n times m of 1 comma y divided by x. And you can carry out the similar steps for the function n also, because n is also homogeneous of degree n, that same degree. So similarly, we also have this, just like this one, n of x comma y equals x to the power n times n of 1 comma y divided by x. Now we go back to our original differential equation, and it's in differential form, we turn it into derivative form. So in derivative form it looks like this, dy dx equals minus of m divided by n. Now in place of m and n we are going to use these expressions. So once you use those expressions, the right hand side becomes this. In place of m of x comma y, you put x to the power n times m of 1 comma y over x, and similarly for n. And then after cancelling this nth powers of x, this is what you are left with. Note that this in its entirety is a function of y divided by x after all. So that means you have first of all turned the differential equation which is in differential form into derivative form, and then you find that the right hand side is a function of y divided by x only. So by definition of homogeneity, this equation is homogeneous, and that is why instead of going through all these steps, if your functions m and n themselves are homogeneous but of the same degree, that is important, okay? Because if the degree is not same, then you can cancel x, but x will be left either here or here, and you won't have the right hand side as a function of y divided by x only. If they are homogeneous of same degree, then this is also a homogeneous equation. So you can go back to examples 2.10 and 2.11 and apply this method to see how they are homogeneous, how the equations are homogeneous. In particular, in example 2.10, you will see that the functions m and n there are both homogeneous of degree 2, and in that other example, the functions are both homogeneous of degree 1. And finally, we have this result, which is this section is all about. So you have your differential equation in differential form, and it is given that this is homogeneous. Then you apply this change of variables to this equation. Y equals Vx. Y and x are our old variables, but this is a new variable V. If you do this and then you transform this entire equation in terms of V and x, so you get rid of y. You can see what will happen from this equation. If you differentiate both sides with respect to x, what are you going to get? Dy dx equals x times dv dx plus v, because dx dx is 1. So you can do like this. You can first turn this equation in derivative form. It will then come like this: dy dx equals something, some function of x and y. So in that some function of x and y, you replace y with vx, and on this side where you have dy dx, instead you write dv dx x plus v. So that's how you get an equation in these new variables v and x. X was already there, v is the new one, and you will find that this new transformed equation is separable equation. So then you can solve it, and that way you can solve the original equation. The proof is very easy. It's just this that I said just now. So you go through the proof, and in the next video on differential equations, we are going to solve 2 examples on this. We are going to turn homogeneous equations into separable equations and then solve them. So let me just end this video here itself. So see you in the next differential equations with those things. Until then, this is me, Lucifer, from A Mathematical Group. Have a nice day.